Hello, everyone. My name is Chen. I'm very happy to present our work, which is done together with Michael and Sven. We all came from University of Zurich. First of all, let me introduce you connectivity query on fully dynamic undirected graph. So input graph is undirected. The connectivity query checks whether there exists a path between two query vertices. For example, here, if we want to know whether there exists a path between the vertices 3 and 9, and the query returns true. That's because there exists a path highlighted here. And the graph is dynamic, which means we could insert, delete vertices and edges. In this work, we focus on inserting and deleting edges. This is because inserting and deleting vertices can be handled easily. Um, yeah, here, let's delete the edge 4 and 8. And and 3 is disconnected from 9, and the query returns false. For example, let's assume we insert an edge between 0 and 5, and 3 is connected to 9 again. As you can see here, even with fix the current vertices, the result can change because the graph is evolving. Let me formally define this problem. Given an undirected graph and an arbitrary sequence of updates, they are insertion deletion of edges. Our goal is to find a data structure that is fast in answering queries, also fast in maintaining itself. There is one real-world application we got to know from engineer who adopted our previous work that is also solving dynamic connectivity problem, and we are happy here to share with you this application. This application is to run simulation to test robustness of power grid. If you want to know more details, you can contact us. So now let's dive into the tree data structures. Here I summarize the common tree-based data structures. They are balanced binary search tree, heap, and spanning tree. Let's look at these data structures one by one. In balanced binary search tree, it contains atoms and nodes, and we can search node in the tree. We can update the tree by inserting and deleting nodes. But however, here the edge information of the graph is missing. Next, let's look at the heap. Similar to balanced binary search tree, here's the tree representation for a heap, and it also contains nodes, and since it returns the minimum over all the atoms. For min heap, we can also insert and delete nodes from heap. Heap does not preserve edge information of the graph. Next, let's look at spanning tree. By definition, spanning tree is a subgraph. It naturally preserves the graph information, which are nodes and edges. And we could also insert and delete nodes and edges. And here, it naturally says spanning tree can be used directly to solve the dynamic connectivity problem. So next, let's move on the data structures for dynamic connectivity problem. I list all the major data structures, and we categorize this data structure into three classes. And on the right hand side, these are the tree data structure they are using. The first is spanning tree. The second is Oloto tree. Oloto tree, later I will explain you, is balanced binary tree. And the third, the big body of class, they are trees with bounded height. And the existing data structure mostly came from theoretical computer science, which means most of them were not implemented or evaluated before this work. So we implement the data structures and evaluate them empirically, and our goal is to understand the data structures. During our evaluation, we look at these three aspects: memory footprint, update performance, and query performance. We spend time to think the important aspects, in the end, we came up with the three aspects. We believe these three aspects are important when we use this data structure in practice. The conclusion is a bit unfortunate. We found that no data structure is robust for the dynamic connectivity problem. So next, let me explain you the weakness of each data structure. So let me start with the simple technique spanning tree, which is the D tree. So spanning tree is simple. It's naturally a subgraph. It preserves the graph information, but one column has two sides. And since spanning tree is a subgraph, if the graph has a fixed structure, that's not good for dynamic connectivity problem, which means the spanning tree has a little chance to have good performance. Why I say that? That's because there exists a big body of graph they have long diameters. The use cases are road networks. And these graphs are worst case graphs for D tree. That's because such graph contain long path. For example, as I show here, why long path is bad for the D tree? That's because when updating D tree or querying D tree, we need to traverse node one after another. For example, here, let's consider one extreme case. We have a line graph, and which contains an n nodes. So we traverse this path, that it D-tree takes linear time, which is expensive. And our experiment confirms this analysis. As you can see here, the bar shows the runtime for D-tree, and the lower the bar, the better the performance is. As you can see here, the path graph and the USA, which stands for road network in the USA, and D-tree degenerate a lot in both of these two graphs. So here is a bit of our takeaway message. The simple data structure such as spanning tree, they do have worst case graphs that do not scale. And next, let me talk about Olotor tree, in short, ET tree. What is ET tree? So we have ET, and we put ET in the tree. This is ET tree. I put this figure, just want to make it relaxing, because we will dive into the technical detail of Olotor tree. It's ET tree. So Olotor, by definition, is we take the Olotor over the spanning tree, as shown here. We start from one node, and we take round tour, and we end up with at the same node. For example, here we start at 7, we go to 8, and so on and so forth, and we pass by 7, and we go to 6, then we end up being at 7. And as you can see here, we start in the Olotor, we start at 7, and we visit second time 7 here, and then we end up to be at 7 again. This is the Olotor, and Olotor tree created a node for each occurrence in the Olotor, and create a node for each of them, and build a balanced binary search tree here. As you can see here, so in the Olotor tree, the number of nodes is 2 times of the nodes in the spanning tree. And as I mentioned before, the binary balanced search tree does not preserve the edge information. So Olotor need additional space to store the edge information and Olotor information, as I summarize here. And what is the cost? Because it consumes more space to maintain the data structure, as I show here. As select 4 graphs for data set, and here it shows the memory footprint for D trees and Olotor trees. As you can see here clearly, Olotor consume at least 2 times memory than a D tree. There are further optimization that maintains multiple Olotor trees, and we can imagine that such optimization demands more memories. So our takeaway message is when we do optimization, we do not only consider amortized cost, we may also want to consider memory footprint if we want the data structure is easy to use in practice. And next, I will talk about the third category and mainly focus on talk about this local tree, which is height-bounded binary tree. And why I want to talk about local tree, that's because local tree is so far the data structure with best amortized cost, but our experiment shows that local trees are slowest in practice. So I choose the the local tree with the optimal theoretical cost, and and we evaluate it with 6.9 million deletion, and here are the runtimes. As you can see here, local tree takes at least 2 orders of magnitude more time than the D tree. So we struggled for a while to understand why a local tree is slow, because it has the best amortized cost. And when we show the runtime of individual deletion, we found that for some deletion, they took much more time than the other deletions, and we call these deletions outliers. As you can see here, there's one deletion takes 10,000 seconds, which is not very practical when used in a real world application. And we did dive into why there exists deletion outliers. And here is our finding. For some deletion, the local trees need to access and modify a massive number of nodes. For example, 500,000 nodes. So there's for one operation. But for tree data structure, the data locality is not good, and the cache utility is also not good. So based on this, the local trees are the slowest in practice. And with that, I want to conclude now. Although it's a bit unfortunate that there are no robot data structure for the dynamic connectivity problem, but in practice, we do suggest to use the D tree for graph with small diameter and solution based on Olotor trees for graph with large diameter. And we plan to extend D tree to make it the first robot data structure and further extend it into databases. And that's all. I'm very happy and I am open to questions.